Metamorphism on the moon, and in particular the granulite suite of rocks that we have, are particularly important because, and specifically in terms of understanding the protolith of these granulite rocks, are particularly important because they feed into a story about how the lunar crust acquired its first primary crust and how crustal formation occurs on the moon. And this is an important story, and this is an important process to understand, because the way in which the moon acquired its primary crust is how we solar system bodies such as moon, Mars and Earth also acquired its primary crust. And so in a way, the moon's geological record sort of preserves a snapshot of the type of geological processes that was probably occurring in the very early Earth as the Earth was still differentiating and building its own crust. So before I get into the metamorphism and some of these rocks, I just want to quickly just mention some of the key lithologies that we see on the moon, and some of the key concepts that I'm going to be referring to. So the moon is a differentiated body. You can think of it effectively as a massive ball of magma in space that crystallized out slowly. And the general idea is that it started as this ball of magma. This is the so-called magma ocean hypothesis. It would crystallize out. So first, as you might expect, you'd get your mafic minerals, your olivines, your pyroxenes start to crystallize. They would be dense relative to the surrounding liquid, and they would start to accumulate and settle and build up a mantle, a mafic mantle. Then at some point, plagioclase would start to crystallize. This would be less dense than the surrounding liquids. They would float and accumulate to form a thick, plagioclase-rich, anorthositic crust. So you end up with a situation like this, where you have a mafic, a mantle made of mafic minerals and an anorthositic crust. And then I might mention in this talk very briefly, if I mention the term creep. This is basically just a sort of a thin layer between the crust and the mantle of the last dregs of crystallization that crystallized and solidified. And creep is just an acronym for the main main elements that are within this sort of layer: phosphorus, the rare earths, and potassium. And it's basically all the residual stuff that that doesn't want to go into your plagies and your olivines and pyroxenes and all that. So a bit later on then, what's also important is that there were these plutonic intrusions into the anorthositic crust that were a lot more magnesium rich relative to the surrounding crust. And then these are known as the magnesium sweet plutons. And the last thing to bear in mind also is that when we're sampling all these rocks from the lunar surface, either through meteorites or through the Apollo collection, that the surface of the moon isn't just a pristine landscape of bedrock. It's been constantly being bombarded by impacts, and it's constantly being gardened and reprocessed. So actually a lot of the samples we have, and this is particularly the case for lunar meteorites, is that they're breccias, they're impact-related breccias. And we also have a lot of loose, consolidated soil or regolith that's a lot of basically mineral debris and broken up rock fragments. And so the challenge really is to sort of take some of these rocks and sort of see what we can say about the sorts of geological processes that are occurring that sort of form these units that we see. And in the cases where a lot of these clasts are very small, or when you're only looking at a couple of mineral fragments per clast, chemistry is a very useful tool for trying to identify apparent lithologies. And this is a classic plot that's used a lot to sort of identify some of these potential different lithologies that small clasts that we study might derive from. And so this is a plot of the anorthosite content in plagioclase versus the magnesium to iron ratio in mafic minerals within a particular class. And you can see in this blue field is where anorthositic crust plots, so very calcium-rich plagioclase, and relatively ferroan mafic minerals, whereas your these secondary magnesium-rich plutons tend to have a bit more of a spread in terms of their anorthosite content in their plagioclases, and they tend to be a bit more magnesium-rich in general. So, granulites. So the first thing to say really is that lunar granulites are not quite the same as terrestrial granulites, in the sense that while they're the result of high temperature recrystallization of existing lithologies, they don't necessarily have that same pressure connotation that granulite facies might have, metamorphism facies might have on Earth. And in fact, people have proposed that actually you get this high temperature recrystallization at quite shallow depths, and also at quite at depth within the crust as well. And this sort of demonstrates the two main areas where you might expect to find metamorphism on the moon in this cartoon here. So in the first instance, when things might be quite shallow, you can imagine a big impact hitting the surface of the moon. The resulting hot ejecta would then be deposited on the surface, and then that would, in a sense, create a zone of high temperature metamorphism on the surface regolith or whatever the ejecta blanket happens to be depositing on. Similarly, you might get some metamorphism at depth where perhaps some of these Mg sweet plutons are intruding into the crust, and that heat is metamorphosing the surrounding crust. And this is then sampled by then large impacts that are then excavating this material to the surface, where we can then sample them. So in terms of what some of these rocks look like, a huge range of sort of textures. And so these are some thin sections for 2 Apollo samples. These are some of the nicer examples where we have some more sort of fresher, not so brecciated rocks. And sort of typical textures range from nice granulitic textures to more sort of poikilobastic type textures. In some cases, so for instance, here you can see a sort of bigger olivine grain and get more of a granulitic texture in between some of these larger grains. But these are sort of quite fresh examples. Mostly what we deal with is more broken up material. And you can see here, this is a thin section here of a breccia where you can see there are distinct clasts with all this broken up material in between. And these individual clasts, this is quite a nice example where some of the clasts are a bit larger, and you can see some nice granulitic textures within individual areas. But perhaps more common, particularly in some of the lunar meteorite collection, is very, very broken up material. And you can see here, you're dealing with really quite small clasts in some cases. And so trying to interpret the geological history of some of these mineral fragments and small classes can be quite challenging sometimes. And also shock is an important factor to bear in mind in some of these samples. In some cases, impact, you can get some impact melting associated with shock, and you can get these sort of glass veins intruding into samples. Also, plagioclase can be highly shocked to the extent that it can actually form a high pressure pseudomorph called mescalinite, which is kind of a sort of a diaplectic glass. So in general, there are 2 flavors of granulites. There are some iron-rich ones and some magnesium-rich ones. And so this is this classification diagram I showed before of AN number in plagioclase versus magnesium number in mafic minerals for some Apollo samples and from some lunar meteorites. And the sort of Fe-rich type granulites seem to plot in terms of the chemistry very clearly in the crustal anorthosite field. So people have suggested that these reflect the recrystallization or of these crustal rocks. Whereas the case for the magnesium-rich granulites is not quite so clear. And this is really where a lot of debate has been within the literature in terms of what these protoliths represent. As you can see, some sort of plot quite clearly within the magnesium sweet field. However, some compositions do stray towards the sort of the fringes and even beyond what we know for sure is the magnesium sweet field based on analyses from the Apollo collection. And this is particularly important then. Some people have argued that these may reflect another type of anorthositic material. And this is really based on some recent work. Really, a lot of the lunar community has revisited a lot of these crustal formation models and refined the picture to sort of more to try and understand some of the finer details of what was going on during this time. And in terms of rather just a simple flotation event like I described earlier, various studies have argued that maybe you've got discrete diapirs of sort of compositionally different plagioclases that are accumulating. Maybe there's some crustal asymmetry. Maybe impacts play a role in some of the lithologies that we see. And so, you know, if some of these granulitic rocks represent metamorphosed equivalents, potentially of some different anorthosites that are not sampled by Apollo, some, for instance, some more magnesium-rich anorthosites. This plays in to this story of trying to understand how the crust is built and what exactly the sort of mechanisms are that go about forming these crustal rocks and how that might apply to the early Earth. So this is some very preliminary data then, and this shows that the magnesium-rich material falls on this classification diagram just outside the Mg suite field, and it's chondrite normalized. This is plagioclase data. This is some of the first plagioclase trace element data to come out of these granulite suite. It's sort of on the fringe between magnesium suites compositions and reported anorthosite compositions. And really what I wanted to sort of show off really, this is sort of the main slide really, is that the power of trace elements to try and resolve between different protoliths. We can see that these black circles here are reported compositions for anorthosites, whereas these orange squares are Mg suite, and you can see that for both samples they fall quite nicely within the anorthosite field. So is this evidence that indeed we're sampling something more anorthositic rather than something that was a protolith that was more akin to these Mg suite type rocks? So does shock, I'll just sort of skip through these final few slides, I guess I'm running a bit late. So we thought about shock, this is based on a study a few years ago we did, doesn't seem to impact trace elements particularly. However, the outstanding question, and where we hope to take this further now really, is to try and understand how subsolidus re-equilibration and how recrystallization affects the trace elements of these. So some very preliminary data versus some published peak metamorphic temperatures versus, for instance, like earth enrichment, doesn't seem to show much of a trend. However, this is bulk rock. These are from pyroxene pairs, and so I think the value really will be to try and look at individual mineral trace element inventories and see how the rare earths behave. Is there evidence of zoning? We know rare earths diffuse quite slowly in plagioclase. Can we preserve evidence of this re-equilibration process? And to what extent can we use trace element systematics of these rocks to say something meaningful about their protolith and therefore about how the lunar crust was built? So I'll just leave these conclusions here. So yeah, basically metamorphism on the moon is a thing. Thank you very much.
Great, thanks, John. So do we have any questions? We are getting a bit over time, but if anyone wants to ask John a quick question. Might even allow you to speak as we're at the end. Okay, Peter, do you want to unmute yourself to ask a question?
John, that's a lovely talk. I remember the excitement when I was in Cambridge back in the, crikey, the 80s. You know, with all the moon rocks coming in and going through the labs. How far do you think that conclusions derived on the basis of the available data set, which is actually fairly small, will stand up if we all go back to the moon in another sort of 5-6 years and start collecting hundreds more rocks and going through them? I mean, is the moon really, I won't say a simple system, but the models are based on a very small data set. Interested to hear your views on that.
Yeah, it's a good question, certainly. I mean, certainly the rocks that we have from the Apollo collection seem to sample quite a chemically anomalous area of the moon anyway. And so there's a lot of mystery in terms of what we're going to find if we end up getting a lot more sample return from, say, the lunar fast side, which is what the Chinese are hoping to bring back. But I think it's quite encouraging, though, that a lot of these fundamental concepts, such as magma oceans, I mean, these were first proposed back in the 70s. And as we've improved our analytical techniques and as we've been able to analyze rocks in greater and greater detail, and as we've been able to add to the Apollo collection through the recovery of meteorites, a lot of these hypotheses have stood up. So I think in terms of the broad big picture stuff, my feeling is that a lot of these things will hold up. I think we're at the point now really of looking more at the fine nuanced details, like I alluded to earlier, in terms of quite what the individual sort of processes were happening. And there's a lot of room for maneuver and a lot of room for debate in terms of some of the fine detail on these things.